Is this thing on? Greetings, machine component designers. I'm having a bit of an internal struggle in that I'd like to be able to reuse these videos, you know, for future semesters if necessary, but at the same time I try to make them real, as if something's happening real time here. Oh, and here's something happening real time. Cece, would you like to come and say hello to the students? Yeah, my daughter's gonna come and show you something that she found. Yep, come on up here. Tell them what you found.
A feather.
What kind of feather do you think?
Turkey?
Probably a turkey feather, yeah. Maybe a gull, but probably it looks like a beat up turkey. Okay, thanks. Okay, so I like to be somewhat real time and say, you know, something that's actually happening right now to make this more real, less just canned and recorded. So whatever, if you watch this in the middle of winter and I'm standing here in Maine, like, and everything's green, well, it is what it is. Okay, we got to go back to our lecture here. Today we're talking about the static failure theories, all right? Now we're not going to cover all of them, for sure. There's no way we can do that, so we're just going to get the ones that matter the most for us, specifically building a gear reducer out of some sort of steel. Okay, so what's up? Oh, yeah, some housekeeping stuff. So now that we're getting into the much more technical part of the class, so the lecture slides are put together. I'm going to talk to you here. The lecture slides are put together using kind of my favorite images and my favorite equations and the best derivations from a bunch of different books, right? So the equation numbers you see, and even different editions of the same book. So the equation numbers you see are not necessarily, won't match up with the equation numbers in Juvenile 6th edition, right? So just be aware of that. So another thing, you know, kind of related to that, is these lectures are not intended to replace the readings, right? I strongly believe that we've got the internet and it's amazing, and you know that's cool, but you still need to read the book, right? I don't want to try to reproduce the book, otherwise just read the book, right? I'm trying to fill in the gaps and make things a little more real. All right, so that's that, I think. And then, oh yeah, don't machine wash a felted wool sweater vest. Some of you may know that, you know, I'm kind of a jeans and t-shirt kind of guy, but you're also supposed to kind of look the part. So in my world, you're gonna wear jeans and t-shirt, but you throw on a sweater vest and you're a professor, right? Take the sweater vest off, you're just a regular dude again. So anyway, I've got this favorite one of my favorite sweater vests. And it's a dry clean only, but like, whatever, it doesn't really matter. So I chucked it in the wash and it shrunk and kind of ruined my favorite sweater vest. So anyway, that's that. And here's a little note about salmon. We're in Maine right now, or I'm in Maine at least. Not really known for salmon fishing, but I like salmon and they're delicious. And you know, if you like fish. But what's up with this, right? Does anybody recognize these? These are kind of the four of the more common. You know, three of the salmon are named by their color, but then this one is named just called Chinook, right? Which is the Native American name for this particular salmon. But what makes it even more confusing when people say what they caught, right? They might say one of these 4 fish, or they might say one of these 8, right? Because all these different salmon have different names, right? This is called the king salmon because it's the biggest, but it's also the Chinook, right? The silver is also coho, pink. So if you buy salmon in a can, that's probably the humpy or the pink salmon. And then of course there's a sockeye salmon, which is a more common one that you sometimes get in restaurants. So there's lots of different names, and you always have to say, okay, what now? Do these guys use the kind of the color names for their salmon, or do they use the other name, or what do they use? So you have to take this stuff out of context, right? Different industries, different places, different professions will use different terminology for the same stuff, and you have to understand how, you know, what language are they using, right? And that's going to come up here very shortly. All right, so today we're talking about static strength. You need to design something, right? In this class, we're going to design a gear reducer. And in other, you know, you might have to design, you know, suspension parts, you might have to design a printing press, you might have to design some medical device, whatever. But it needs to be strong enough, right? But the best thing you can do is build some parts, build some prototypes, and test them, right? That's what we did in ME 201 when you guys were freshmen, to actually test the thing and see when it breaks, all right? But this isn't necessarily practical. You know, if you're a small company, you can't build thousands of these to test hundreds of them, right? That's too expensive. So it's really only warranted for large quantities or when failure is very expensive, right? So if it costs a lot of dollars or people could die, you have to test the parts, right? You can't just design this stuff based on theory. You have to actually test the parts. So what are we talking about today? Static failure theories, right? Theories. So if you really need to know, build the prototype, break it. It's no good unless you know when it breaks. But if we don't do that, and we're going to design based on theory, at least for starters, we need some way to efficiently use published material strength values, right? We'll talk about that in a sec, right? It might be loaded in torsion, might be loaded in bending, might be loaded in compression, might be pure tension, might be some combined loading situation, right? You have to say, how is this thing actually loaded, and compare that to the published values somehow, right? So, what is this need for static failure theories? Yeah, I just talked about this a little bit. You need to compare some published strength, right? So this is published. Wow, that's terrible. Whatever. And this is based on your design, right? So you have to be able to compare those things, right? But it might not be simple, pure tension. Right, and so we'll talk about that a little bit. Whoa, it's raining flowers here. Holy cow, there's purple flowers flying everywhere. Failure theories propose appropriate means of comparing multi-axial stress states to a single strength, right? Because this is usually tension or a pure tensile load, right? And this is your part. And we have to be able to compare your part. And so we have to come up with some way to say what aspect of the stress state, right? You've got this stress element that, maybe looks like this, maybe looks like this, maybe looks like that and that, and then that and that. How do I compare this complicated stress state? Or which part of these is critical, right? Is the shear the critical part? Is the normal tensile stress the critical part? Is the other normal tensile stress the critical part? We don't know. Now, some failure theories have gained recognition of usefulness for various situations. This is a very important statement here, all right? So, first point, all models are wrong, right? That's why it's called a model, right? We know. Let's go back to here for a sec. We know that steel is made out of little crystals, some iron, some carbide, some ferrite, some all this other stuff, right? And then close center or packed or, face center cubic or whatever. We're not accounting for all those little intermolecular forces. We've got some model that we're using to guess or predict what's going to happen, right? So this is a model. All models are wrong. It's important to understand that. Some of them are useful, right? We are not going to solve from first principles what happens inside the metal. We're not. We're going to make a model. We're going to use a model, all right? So the first one, maximum normal stress theory, or the principal stress theory, okay? And so that's just saying when the maximum normal stress, right, or the principal stress, so I draw my Mohr circle, when that biggest stress, let's draw a Mohr circle here. So let's just say we've got some Mohr circle that looks like this. And so this is sigma, that's tau, and so this is the max normal stress is there, right? So if that gets bigger than the tensile stress or the tensile strength, which is published of my particular metal, then that's when it's going to fail. All right. So compare the largest principal stress to the yield strength, right? And this is often the first theory that we learn because it's the one that makes sense, right? Well, how hard do I pull on it? It breaks at this load. All right, now I'm going to load it up like this. It'll break at this load. All right, so that's really easy. So in the Salmon factor here, this is all called the Rankine failure theory. So maximum normal stress, MNS, or the Rankine failure theory, right? And this is a theory. What does this look like? All right, so if I've got something in pure tension, right? And so this one here on the right is pure tension. Uniaxial tension, I'm only pulling on it in one direction. And then here is one that is pure compression, right? And so if I plot these two things here, so this is the tension in one direction, tension in one direction, not the band. I wouldn't recognize there's music if I heard it. And then this is the other direction. Right? So if I just look at those, as long as I am below its tensile strength in this direction, and as long as I'm below its compressive strength in this direction, right, my part should survive. Right? So I'm not exceeding, nowhere in this part do I exceed its tensile strength in tension, and nowhere in this part do I exceed its compressive strength in compression. In which case, it should be fine. Right? And so we get this box, and as long as when I plot my first and second principal stresses, I fall within the box, I should be good, right? And this does actually work pretty well for brittle materials. What happens if we compare this to some ductile material failures, right? So what these dots are, these dots are experiments. Dots are experiments, right? And here's our box, right, where I always stayed below. This is actually a non-dimensionalized stress there. I'm just dividing the stress by the yield strength. So sigma over SY equals 1 is its, so that's its like safety factor of 1 right there. So anyway, so as long as I keep this below 1, or as long as my stress stays below the yield stress or the yield strength, right, I should be fine. But when I plot that, here, actually, I exceeded SY, and then here, it failed before SY, right? So now I'm thinking maybe this normal stress for a ductile material, the maximum principal stress theory, maximum normal stress theory, maybe it's not so good, right? For very simple loadings, for specific loadings, this could be a good model. But in this situation, for a ductile steel, for instance, these data don't match up, right? Here, no big deal, because if I'm designing somewhere in this box, I'm still safe. But if I design a part out here, this design would fail. Right? Okay, so let's keep moving here. Keep her moving. Now, what about this? The maximum shear stress theory, right? And I don't like to read these. I don't like to read slides to people. That's like the most annoying thing, but I'm going to. Theory. Yielding begins when the maximum shear stress in a stress element exceeds the maximum shear stress in a tension specimen of the same material when that specimen begins to yield. What the heck does that mean? All right, I gotta wave my hands a little bit, otherwise I don't feel like we're making sense. Okay, so in 307, right, we take this tensile specimen and we pulled on it like this, right? And it eventually broke. And I said, yeah, but what if it wasn't the tensile stress that actually broke this thing? What if it was actually the shear stress? Which means I'd have to draw some more circle and figure out, as I was pulling on it straight this way, if I rotated that stress element somehow, flowers flying all over the place again. If I rotated this stress element such that I maximized the shear stress for the same loading, maybe that's the critical thing, all right? Oh, look at that. Can you see that back there? Yep, she's breaking into the shed. So that's kind of what I'm saying. Even though I'm loading this in pure tension, there are some shear stresses that happen in here somehow. And so maybe I'm going to compare the maximum shear stresses in my part that I designed, and I'll compare those to the shear stresses that were in the tensile part when I tested it in the 307 lab, and we'll compare these. Okay. So for a tension specimen, the maximum shear stress is sigma 1 over 2. Okay. At yielding, when sigma 1 equals sy, the shear stress is sy over 2. Let's maybe draw a quick picture of that. Do I have a quick picture of that? Yeah, I do, right? So this is my tensile yield strength, right? But this is tau max, right? In that same, so if I would have rotated that stress element, that would have been my maximum shear that I could have got, right? So I want to compare the maximum shear in my part to this maximum shear here, right? Another way to plot that is like this, right? That this kind of, that's another way to look at it there. So I wonder, do I have another more circle? Yeah. So let's draw a better picture of this. Okay. So what am I trying to do? Oh yeah. So let's say I've got some stress element, right? Oh, I got to draw it like this. So, and I put it under some tensile load, right? Well, what does that Mohr circle look like? I better draw. This is sigma. This is tau. Well, if I draw this red one on here, then I've got uniaxial tension, so it just looks like this, right? And then there's no shear, right? So I don't go up or down at all. And then I've got no tensile stress, no normal stress in the other direction, so that's 0 and 0, right? So this is sigma, let's just call it x. So this is sigma x comma 0, and this is sigma x. This is sigma y comma 0, right? But there is no sigma y, so it works out to be 0, 0. Then I draw my Mohr circle, and that's my Mohr circle. This winds up being tau max, right? But then I'm like, ooh, okay, so what if we did something a little different here? What if I did in blue, let's draw a different stress element. Let's draw this. So I've got some sigma x, and I've got some sigma y, right? Like this, right? So now I've got tension in two different directions. Okay, let's draw that Mohr circle. So I draw this, and then I draw this, which also exists, and then I draw my Mohr circle. Okay, so that would look like that. Now we need to do a quick little review of your Mohr circle stuff, right? Remember, Mohr circle is where I rotate this stress element, right? And I say, how could I rotate this? Is there any way to rotate it and I still wind up with some shear stress, right? And that's what Mohr circle is. But so far we've only done that in plane. If I take this and rotate it out of plane, right, I might wind up with some, I can rotate it so one of my principal stresses goes away, and then I can get a much higher shear. So what happens when we do that? So if I rotate it out of, so this is in plane. If I rotate that stress element out of plane, I get something, oh, that's interesting. So this one is in plane, and this one is out of plane, right? So that one's out of plane. So look at that. My tau max is exactly the same, right? So what does that mean? That means if I have positive stresses, so this is both positive stresses, it goes in there, right? So in that sense, the maximum shear stress theory and the maximum normal stress theory look a lot alike. But what if I drew one, and so I'll do that one in black here. Maybe a little bit bigger, right? Like that. So what if I had another element that looked like this? And it had a negative, it had a compressive stress there like that, right? So that means that I would have still the same one here. Sigma x and sigma y is now compressive, so now I've got a point there and then a point there, right? So now all of a sudden, right, so much higher tau max, right? There's a much higher tau max there. So all of a sudden, even though, you know, well within, so this is within SY, and this is within SY. They're both within the yield stresses, but the combination of them resulted in a much higher shear. All right, so this part would fail. How do we plot that? Whoop, back here, right? So a combination of high and low. Combination of positive sigma 1 and negative sigma 2 causes earlier failure. Right, so that's along this line right here. Okay, so that's really, really important. All right, again, a model, right? What is this based on? Oh yeah, so the maximum shear stress and a tension test specimen of the same material when that specimen begins to yield. All right, so this is my hypothesis, this is my theory, my model. So let's see, what does it say here? So for any stress element, use Moore's circle to find the maximum shear stress, right? We gotta find maximum shear stress, right, of that stress element compared to the maximum shear stress of SY over 2. So that this is kind of like the shear strength, right? Because in pure tension, remember the red one, right? This is SY. And this is up here, SY, the shear yield strength, right there. And the shear yield strength is the radius, whereas the yield strength is the diameter. Therefore, the shear yield strength is half of the yield strength, right? Okay. So, so tau max, right, is sigma 1 minus sigma 3 divided by 2, right? So it's the radius of my circle. The diameter of my circle, this is diameter. Oh, redo that. This is the diameter. And so this makes it, the 2 makes it the radius, right? So as long as my radius is less than the shear strength, I'm fine, right? If I want to compare a safety factor, right, I could write it as one of these, right? I just have to make sure that, that my, well, you know what? I think this one makes the most sense, right? Algebraically, this makes the most sense, is that, that, I totally lost my train of thought here. This is my shear strength, not the tensile strength, this is the shear strength, and this is my design max shear. All right, and then I have this little note here. This is what confused me. What's the difference between these two expressions up on the top? Well, I just multiplied by 2, right? So basically, the diameter has to be less than the yield strength, or the maximum shear has to be less than the shear strength. It's the same statement. Okay, that's important. All right, maximum shear stress theory. What does this look like? So let's draw some pictures. Let's draw them, I don't know, for no good reason, with black. Sigma A is greater than sigma B, which is greater than 0. Okay, so how does that look? So sigma A is out here, first principal stress. Sigma B is right here. and they're both greater than 0, well, that's what that Mohr circle looks like. So let's call this sigma, and we'll call this tau. And then, but my biggest one, right, my biggest Mohr circle is really this one. So this is tau max, right? It's important to note that in this case, tau max is only a function of my first principal stress, right? This determines the biggest circle, right? So sigma A determines the biggest circle. So as long as sigma A is less than the yield strength, I should be good. Okay, case 2, sigma A is greater than 0, sigma B is less than 0. All right, so let's draw that. Sigma tau. So if I have positive in one direction, negative in the other direction, and I draw this one, okay, so now sigma A and sigma B both contribute to the maximum shear stress, right? Because the farther I move sigma B to the left, the bigger my circle gets. In this case, the upper case, moving sigma B around doesn't really change my big circle, right? But in the second case, it definitely does. And then in the third case, right, where they're both negative, so this is tau and this is sigma. If they're both negative, it's kind of very much the same as case 1, where my biggest circle is really determined by just the bigger compressive stress. Okay, good. So again, this is the design envelope. Where as long as my design, right, so this is my design load, right, goes like that. This is where I would expect failure. Failure expected, right? And then so the safety factor winds up being, so strength, and this is stress, right? So my safety factor becomes strength over that. So remember, case 1, it's only dependent on the first principal stress. Case 2, the negative principal stress matters. Case 3, it's only determined by the bigger compressive one. Okay. What's going on there? Next page. So if I compare that to the data, this looks much, much better, right? Still conservative, right? Because I don't go all the way out there, but it's much, much better. So this is getting long. This is way longer than I thought it was. But it's these topics here that are really going to kind of drive the rest of the semester. So sorry that it got a little long. Okay, so that's better. All right, next up here. Ooh, yeah, distortion energy failure theory. All right, distortion energy. Now this gets long, but we're going to go through it fast. This is based on the theory that if the strain energy is divided into hydrostatic volume changing energy, right? So hydrostatic meaning it's just if I took this cube, where is the hydrostatic? Put cube at bottom of pool, right? So your ears hurt, right? It's getting pushed on or stretched equally in all directions, right? And then there's another one that's distorting it, right? So smooshing versus distorting. So in other words, you could think about this as pressure, and you could think about this as viscosity, right? So if they're all equal, so this is the average, and then this is the sigmas minus the average, right? So one of these only let me show this like this. So the hydrostatic one, I'm like smushing this thing, right? Smushing or stretching it equally from all sides, right? And then the other part is deforming it like this. Okay, so I'm actually distorting the cube, right? For this one, the cube remains a cube, but for this one, the cube gets distorted. So let's go back and look at the theory. Theorizes that the strain energy is divided into the hydrostatic, the one on the left, and then a distortion energy on the right. It's the distortion energy that really causes things to break. All right, now let's go through this fast. Oh yeah. This is also called the von Mises stresses, or von Mises distortion energy, shear energy, the octahedral shear stress, blah, 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 blah. Okay, I'm gonna make a separate video for this. No, this is important, right? So notice it's called von Mises. Some of you maybe have at some point done a finite element analysis in SolidWorks. Like, I designed this part for the Baja team, or the Formula car, or for the human-powered vehicle, whatever, and you designed this part in SolidWorks, and you did a finite element analysis, and you got a nice color plot with red spots and green. It's mostly green, a couple red spots. I'm like, oh yeah. Right, this is the danger of these finite element software packages. You have no idea what you're looking at, right? And I'm not disrespecting you, but you have no idea what you're looking at. Because if you look in the fine print, like down on the bottom of the little display, it's showing, it's the von Mises stresses. What the heck is a von Mises stress? Let's talk about this. So again, we, didn't I just do this? Yeah, okay, so I'm really interested in the distortional component here, right? Okay, so the average stress, right, is the sum of the three stresses divided by 3, right? That's how we take an average. And then the energy involved in that, right? The energy is 1/2 times the strain times the stress, the strain times the stress, the strain times the stress, blah, 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 until, and I can shuffle this thing around until I get something that looks like this, right? The energy is 1/2 times some other stuff squared. 1/2 something squared, right? Oh, that's like a spring. The energy stored in a spring, 1/2 kx squared, right? This looks a lot like this, right? Causes a spring effect. This is the stress. Combined, those two make some sort of displacement. So it's 1/2 kx squared. So this is like a spring. I'm storing energy by deforming this little cube of stuff, right? Okay, live, this is painful. Online, too painful. So we're gonna skip that, right? Until we get all the way to, okay, so we do a bunch of stuff, until we get something that looks like this, right? Right? That thing there looks like the plot of an ellipse, right? If I said, the radius is, we've got this quadratic term, a cross term, we take the square root of all that stuff. That looks a lot like an ellipse, and this is an ellipse with in a rotated coordinate system, all right? If you remember that from your algebra class in high school. So anyway, we can convert this, right? We can take this sigma prime, so this is using the principal stresses up here, principal stresses, but I can convert that back into just my original X and Y normal stresses and then the shear, right? So I can take the shear in the original coordinate system, right? Why is this convenient? This is so convenient. I'm gonna do this in this green guy here, right? This is so convenient because it's in terms of my original coordinate system. That's so important. That I take my X component of normal stress, my Y component of normal stress, and my shear in the original coordinate system, and I can plug it in here, and I get this, right? So this is an equivalent stress, right? It's not actually a stress. I am not stressing it in this direction. It doesn't even have a direction. This is scalar, right? But it's an equivalent stress that allows me to compare the energy resulting, the energy that's distorting some cubical element of my material to a stress, right? I'm equating a distortion energy to a stress, and then I can compare that stress to a strength, okay? And this is huge. So when you do your little SolidWorks model, you see these von Mises stresses, what the heck are you doing? You don't know. But now we kind of do. I'm taking an equivalent stress, a single equivalent or effective stress. It's not a real stress. This is an equivalent stress. It's a stress that has the equivalent distortion energy as a pure tensile stress. All right, and then we compare that with our strength, and that gets us our safety factor. Wow. All right, what happens if we compare that to the data? Whoa, that looks pretty good. That looks really, really good. So this model may not be right, but it's certainly pretty useful. Okay, so I like this one. Now a couple more little things. Shear strength. What if we plot a Moore's circle? Let's do that. We'll do it in black. I totally picked the colors arbitrarily, but so if I plot a Moore's circle for pure shear. So pure shear, what would that look like? Oh, wait, hold on here. This is sigma. There is no sigma for pure shear. It's just shear, right? So I would draw 1 point up here and 1 point up here, and then I draw this like this, right? So this is what the Moore's circle for pure shear looks like. And I know that, yeah, right, we'll just leave it at that. So here is sigma 1, and here is sigma 2, right? Sigma 1 and sigma 2. And I know that the radius, the shear strength, is exactly half of the difference in the normal stresses, right? Because it's just a circle centered on the origin. All right. Yeah, this is, you wouldn't believe how hard it is to do this without waving my hand simultaneously, but we're going to skip this. If we look at pure shear, right, we would, if we believe the MSS theory, right, we would discover that, that the shear strength is exactly half of the yield strength. So right there would be where we're operating, right? The shear, so in pure shear, right, we have equal and opposite normal stresses. So if we plot equal and opposite normal stresses, right, these two are equal and opposite, and that exactly equals the maximum shear, does it? Yep, it equals the maximum shear. And so we wind up with a shear strength that's exactly half of the yield strength. Okay, fine. But if we say, actually, it doesn't fail until here, doesn't actually fail until here, right? Then we discover that there's a square root of 3 that pops out of this, and we discover that the shear strength is actually 57% of the yield strength, right? So which do you use? One is more conservative than the other. We'll talk about that more later. This video got way too long, sorry guys. Hopefully you watch it or at least read the stuff. Yeah, there we go.